All right. Which one? This? Yeah. Okay, let's start our first session for today. So our first speaker is Ryan Tibshirani. It's a great pleasure to have him. Ryan is a professor here at Berkeley in statistics, and he has just told me that he had been knighted, and that means that we have to address him as sir from now on. Just kidding.
That was
he wasn't, I think, being fully serious. In any case, Ryan had been a professor prior to that at CMU for quite some years, and he has done a lot of work on various aspects of statistical inference and optimization. So, yeah, it's really great to have him.
Thank you. All right, thanks, Misha. Thanks for inviting me, guys. I'm happy to be a part of this. I'm excited. I think yesterday was awesome. So I think that this is hopefully going to turn out to be somewhat complementary to Nati's talks. So I'm also going to be doing a review of some of the literature on prediction. My talk is going to be, let's say, slower and probably somewhat simpler. So hopefully either all of or almost all of the statements that I make, I'll be able to prove for you guys. So I'm just going to give you an outline. I'm going to start off with just some comments and an intro about the kind of models and the risk metrics that we will be thinking about. And this is from a stats perspective. So you'll hear some high-level commentary in that part. The second part of the talk, this is going to be across today and this afternoon. The second part of the talk is what I would call fixed X decision theory. So this is some classical statistical theory on prediction, which I actually think, my guess is that most, or at least let's say a good fraction of the people in this audience haven't heard of. It's not, I don't think it's super well known in machine learning, so I think it'd be fun to be able to share that with you guys. The third part of the talk is to compare two perspectives, and I'll make it clear what I mean by fixed X and random X in the intro. And to contrast them into this part is maybe also going to even be interesting for statisticians that know the fixed X decision theory well, to try to point out that for most of the period of time in which statisticians were working on this, we'd thought that these two models, data models and error metrics, are actually very similar, so that this was a good proxy for this. But I'm going to argue in this part that's not really true, and a bunch of modern settings of interest. And the last part is going to be about revisiting a concept that I introduced in the second part, which is a measure of complexity called degrees of freedom. So that's the outline. So let me just start off with some high-level comments before I introduce to you guys the models that we're going to work with. Statisticians have been thinking about prediction for some time. I think that some of these aspects of statistics have not made their way into mainstream machine learning as much as other aspects. I think people in machine learning obviously know maximum likelihood and a lot of the estimation theory very well, and various other parts of statistics. I don't think that the literature on statistical prediction is maybe as well known. I would say that statisticians are very opportunistic when it comes to studying prediction, which means that I don't think that there's one framework that we use that we would say this is the framework to describe prediction. Rather, it's, certain tools work well in certain situations. I'm going to describe a framework, which sometimes gets called statistical decision theory. It's kind of a bad name because there's nothing really about decision making in it, but it's the name that was given classically. And I just want to kind of say at the outset, it's not the theory of prediction statistics. It's one that I think is quite interesting, and like I said, maybe interesting and new to some folks in the audience who come from an ML background. So let me introduce some of the models and the metrics. These boards are darker. I don't know if you guys can see them. Do we have a way of turning lights on here? No? Okay. Hopefully you can still see here. Hopefully my pens don't die on me either. That's a good one. So let's talk about models and metrics. This will be the first part of the talk. Oh, I forgot to say, I'm going to leave this link up here. I wrote some notes that go along with what I'm going to be saying on the board. You can find them at this link. If somebody can check this link to make sure I didn't get it wrong, to make sure it works. Okay, good. So that way you don't have to write anything down. And if you just want to listen, you can check these notes. These notes were kind of somewhat hastily assembled between lecture notes and papers and some various thoughts I had not written down before. So no apologies if they don't read, as well as like an actual paper. But you'll get the main idea from them. So let's talk about models and metrics. So already, I think we're going to see some contrast to what Nati talked about yesterday. And I think part of the goal I have for these next, these lectures is just to point out some interesting differences. Not to say that one perspective is superior to the other, but that they have some interesting differences. And I think that they both have their own strengths and weaknesses. So a model that I would call the random X model for prediction is, I think, it's probably the only model that people in machine learning would recognize of the two I'm going to write. The second one would be almost unrecognizable, and this is the one that Nati talked about, which is that I have XY pairs that are IID from some distribution. I'm going to suppose that my features are p-dimensional, and that my responses, sometimes you'd call this maybe a target or an output in ML, they're real valued. So most of my talk is actually going to be focused on the case in which y is continuous rather than binary. That's another difference, is that a lot of the classical theory in stats does not consider classification kind of to be the first problem that we attack. It's actually regression. So this is the random X model. I just assume that I have IID pairs from some distribution. Doesn't at this point matter what they are. And I'm going to build a predictor. I'll call it f hat to predict y from x, and I'll measure its risk in some way. Okay, that's my training set. So I'll get to the risk metric in a second. Okay, should be very familiar to you guys. Here's a different model, okay, which I can point out books in stats that have been written with either model as kind of the basis. And I would call this the fixed X model. Sometimes people call this the fixed X signal plus noise model. Okay, and that's that I can write my responses as some function of my features, or my covariates, plus noise. These guys themselves are IID. The errors themselves are IID. And they're drawn from a distribution with mean 0 and variance sigma squared. So this is my notation for saying that they have mean 0 and variance sigma squared. If I had a normal, I'd put an n in front here, but I'm going to leave out any qualifier in front. This just means mean 0 variance sigma squared. Okay, and the last thing, by the way, is that the features are fixed. Okay, so that's the fixed X signal plus noise model. Like I said, there's, you can find books written in this framework and books written in this framework. So I want to start off with just, oh, by the way, I hope this is going to be somewhat interactive. I don't have a ton of material to cover, so hopefully we can get lots of questions in. So let's start off with a question. Who thinks that these two models are different? Okay. Who thinks that I can recover this model from this one?
So what are you trying to do in the model? Because it's saying like one, you're trying to like predict over the whole distribution. The other, you're trying to predict with a fixed set, or are you trying to like come up with a function that's going to work well for different?
Yeah, it's a great question. What I'm trying to do will be made clear when I write down the error metric. But in both cases, you can imagine I'm trying to build a predictor, which is a function of x. So it maps RP to R. So let's just say that's my goal so far. Let me probe, see if I can probe you a bit more. Let's suppose I just wrote down epsilon I comes from a distribution with mean 0 and variance sigma squared. And let's just suppose I told you they were independent. Who thinks that I can recover the second model from the first? Sorry? Yes. So if I have this model and I condition on x, okay, then I actually get this model with independent errors that have mean 0 and variance sigma squared, right? Because I can just define f to be the expectation of yi given xi. I can define epsilon I to be the difference between yi and f of xi. Okay, these are going to have mean 0 by construction. They're going to have, I can call their variance sigma squared, doesn't matter. Okay. So I shouldn't have put the sigma squared there for this statement, but and they're going to be independent because I have independent pairs, right? So whatever I do on one I is independent of what I do on another j. So in fact, by conditioning and just defining the regression function like this and the noise like this, I can think that I have a signal plus noise model with independent mean 0 errors. So there's no loss of generality if somebody tells you that they want to write a model like this in statistics, let's say. Okay, once I say that they're IID, and part of that is that they all have the same variance, that's actually different now. Now we have a different model. Yeah, Nati?
I think it's important to also say what you want to do here, because typically in the second model, the most you can hope to do is get f hat of x. And in the top model, they would think that you want to generalize to out of distribution, out of sample x's. And then,
But in either one, we can do either. And I mean, I can write down a risk metric for either.
I don't see how you can.
Let me. Well, I give you a bunch of x's, right? You train a predictor. I could still ask you to make a prediction on a different x. It's a function of x. So I could still ask you to generalize, right? There's no reason that that's like against the rules of this model. But it's maybe not the most natural if I'm thinking of x as fixed. I agree. So what I actually mean is that it's non-random. It's deterministic.
So it agrees, for example.
No, but it could also be, doesn't have to be. It could be that it was random and I conditioned on it. So I'm actually not treating it. It was sampled from some distribution. I conditioned on it. I'm not actually in anywhere in this model going to incorporate the randomness in X. Okay, it could be either designed or sampled and conditioned on. So I guess the point I'm trying to make is that the most offensive aspect of the signal plus noise model should be that we are treating the errors as IID. Not that they're independent with mean 0, but they're IID. And that is actually quite different from having IID pairs of features and responses. To assume that this thing, once I condition on X, is IID. So what does that require? So for that to be true, right, if I had this model and I were to condition on X and I were to see if I could reduce it to this model, I would do this construction. But IID, the IID property of the errors requires that the errors are independent of the X's. That's the way in which I would be able to conclude that the X's were IID. Okay, I claim that this is quite a bit farther than what we've assumed in this model. Can somebody tell me why this is now like a real assumption that we should be questioning anytime we write this down?
Well, I mean, in learning, the case of like uniform noise on the labels is a lot easier than agnostic noise. So it's kind of like something that we're used to, I guess. Like in at least like impact learning, supervised learning.
I think that that's getting at the point I'm trying to make. I'm trying to ask about what role are we assuming the features play if we're actually going to be assuming the errors are independent of the features.
Is it implying causality or something?
I don't want to go so far as to say it's implying causality, but what it's implying is that there are no omitted variables that are correlated with X.
I guess
right?
One example is like, say that someone gives you the F, right? Then you can just like measure the F, the quality of the F, if things are IID, by the correlation with the actual labels that you've seen. Whereas if the noise is dependent on the input, then there can be even the correct F might score lower in predicting the labels than some F prime.
Yeah. I think we're all talking about somehow qualitatively the same phenomenon. There's a hand up back there.
Yeah, I wanted to ask, do you strictly need the IID assumptions? Because in some settings you can get away with just say independence and some sigma, some Gaussianity.
That's right. Yeah, I mean, I don't actually need, I mean, you're right. In some settings, I don't need IID. And if they had different variances, if I knew what the maximum was, I'd be fine. So, but I want to write down this model just to kind of contrast it because it's so common. Yeah.
When you say this independence between epsilon and X, do you still assume X is fixed?
So the statement is that if I had data from this model in which both X and Y are random, and I conditioned on X, when would I be able to write down a model like this? Where I could write Y as f of xi plus epsilon I is IID with mean 0 and variance sigma squared. And the answer is I can do that when epsilon I and xi are independent. So when the difference between yi and its conditional mean of given x is independent of x. That's the statement. So that's what's required to get the IID property. And I just want to kind of make this very salient. Let's suppose I told you that the true model, true drivers of y were x and z. Right? In this case, if I called this the error, even if we're being nice to ourselves and we said that g had mean 0, g of z conditional on x had mean 0, right? For this to be independent of x requires z and x to be independent. So it means that if you had any variables that were relevant for predicting y that weren't included in your model, they have to be independent of x, which is a very strong assumption. So I think of this as being no omitted variables. All the relevant variables for prediction you've included. So that's certainly not assumed here, right? So that's like an important difference to make at the outset. Yeah.
I mean, maybe another way to say something is you're kind of assuming that the uncertainty on the label doesn't depend on the features, right? Which is seems very unrealistic, right? Because in sort of practical situation.
But we're talking about the true model. I agree that would be we're not talking about the uncertainty that I'm deriving somehow from my estimator. We're talking about in the population. I agree it's unrealistic, right? But we're not talking about uncertainty that I would be deriving from f hat, right? I'm talking about in the true model.
Well, you see something, whether it's a cat or a dog, and you're saying the accuracy of my prediction whether it's a cat or a dog doesn't depend on the image.
Not of the prediction, of the best possible prediction given X, which is F. Some oracle, right?
It can be true realistically if it's a completely deterministic thing.
That's not true. I could just have, a regression function with independent errors drawn around it. It's not deterministic. It still has this property.
Like there are cats and there are dogs and there are cat dogs, right? You're saying there are no cat dogs. There are no dogs which look similar to cats.
No, I'm just saying that the amount of uncertainty is the same regardless of where you are in the feature space. So it's not saying that there's no uncertainty.
I think maybe like there's a contrast here because the way I think you think of the error here is maybe different. It's the way, at least sometimes in machine learning, where and this goes back to this approximation error and actual uncertainty. And so if I think of the error as actually capturing that some kind of stochastic error, but just this is, I'm going to use only a certain maybe restricted features or restricted class of predictors. Like the way I'm thinking of it, at least machine learning, is X is an abstract object, like an image. And Y is always a deterministic function of X. There's no uncertainty. It's just that it's possible that based on the features that I use, I cannot completely predict the label.
That describes some machine learning problems, but it can't describe all machine learning problems.
I would argue that describes most of.
Well, are you talking about classification in particular? Because we can write down many regression problems in which there's no way that the labels.
I think that most is about classification of some sort.
Yeah.
Classification, I don't know. Translation, except classification. There is a classification document.
Yeah.
But yes.
So I would say that describes, certainly like a large number of ML problems of interest, but I would call that infinite SNR, right?
I agree, but what I'm saying is that if you think of it that way, then you can still think of it in terms of error. But now those errors are not really coming from pure uncertainty. They're and I think I'm just trying to chime into
I see.
to Misha's view.
Yeah.
And then it doesn't make any sense that they're independent.
Sure, I understand. Yeah, the errors here are the errors that you would encounter with the best possible model with respect to your features. If Y is deterministic, then that's really an approximation reflection rather than a reflection of stochasticity in sampling or something like that. Yeah. Was there some other hand up? I didn't see one. Okay, given these differences, what I want to do is talk about some what I would consider classic literature in statistics that studies prediction in this model. And then I want to connect it back to this model towards the end of the lectures. Okay. This model is more restrictive for the reasons we just said. The error metric that's natural in this model is also different. All that said, there's some powerful conclusions that we can draw from thinking about prediction in this model. And that's what I wanted to share with you guys. So those are the models. Let's talk about risk metrics or error metrics. Okay, so in a random X model, the most natural model for risk would be what I would call random X risk. And that R is supposed to be a subscript that emphasizes that. And this is defined by saying, if I were to give you a new pair X0, Y0 from the same distribution that's independent, it's IID to these training points, then we're going to ask what is the squared error, for example, that I would encounter if I predicted Y0 from F hat of X0. Okay?
Yeah. So suppose I wanted to think about a fixed X, which is a grid, and I'm willing to buy your epsilon independent of X assumption. It's still not obvious that you can get it from a random X model. Like how do you, there isn't a random X model that when you sample will give you
Can you repeat the question?
Yeah, the question was, so I said that somehow I can deduce fixed x from random x by thinking of sampling, conditioning on x, assuming this. And Siva's comment or question was that, well, there are some fixed x problems that is not described. For example, like if I designed an experiment where I sampled out a grid. I agree. Yeah, so basically this encompasses, different types of problems, some in which x is designed, some in which x is sampled and I've conditioned on it. Yeah, I'll go back to the comment about experimental design because I think that's actually an important one for the motivation of why people study this in statistics. Okay, so this is hopefully not like controversial for anybody. This is a very natural notion of risk. I'm going to talk about squared error predominantly, but everything I say will actually have a counterpart if I replace squared error by a Bregman divergence. So it can encompass things like cross entropy, for example, what statisticians call binomial deviance in a classification model, or other negative log likelihood functions associated with exponential families. So the squared error assumption is just for simplicity. That's okay. Actually, I want to say one more thing before I move on to the natural notion of risk in this model, which is that this expectation is over everything that is random. Which means that it's over the training set and the test set. In my definition of risk. There's another difference, is that even in the literature in statistics in which we study this model with this metric, we mostly tend to integrate over the randomness in training. So we're not talking about the error of a fixed predictor f hat that's being integrated over a test point. It's actually integrated over the training set as well. Okay, this is also an important difference. I think we could go on another tangent and talk about this for a while. Some of what I say will actually apply to what I would call training conditional risk, which means it's like what we looked at yesterday, which is where I consider f hat to be fixed in this expectation, only integrate over x, y, but not all of it. So the randomness in the training set's important for some of the conclusions. Okay, and the other metric for risk that we're going to look at is what I would call fixed x risk. It's the one that's most naturally associated with this model. I think that's what you were getting at earlier, Natya. I was saying that really either risk metric applies to either model. This one I could ask you in this model to measure risk this way, but it's maybe not the most natural. You seem to be confused by that.
That requires distribution over x, and in the fixed x model is no distribution.
Okay. In the case in which somehow x was sampled, it was conditioned on for this, right? Then I can, another statement is that like I could put down a uniform distribution if it's been designed. So in a grid design, it's very common to say that I'll just consider x to be uniformly distributed over, convex hull containing the grid. No, not necessarily, because I've treated x as fixed somehow in training. I mean, I'm not really in a random x model per se. I mean,
what do you mean that it's some? I mean, if you're
if I was in the fixed x model and I really wanted to measure risk in this way, I'd have to come up with a distribution for x. I can either do so by specifying one, like a uniform distribution in the case of an experiment, or maybe I have one that's natural if I actually believe that I had conditioned on x in order to arrive at this model. But I don't want to go too deep into that because I want to think about this risk being associated with this model and a different risk being associated with this model. So I'd certainly take the point that that the most natural risk metric in this model is what I would call fixed x risk, which is, this is going to look a little bit strange to the ML folks in the audience because I don't think that this is something that is very common. So I'm going to condition on x in case it was random, and everything that I'm going to say for the rest of the talk is going to have like a condition on x just to accommodate all cases. Okay, if x was deterministic, truly deterministic, then it wouldn't do anything. If x was random in sampling and I had somehow used this model, I would condition on x. Okay, so what is y star I? That's what I have to tell you. It's a label that exists at the same x that I saw in training. So I think about it as if, what happens if I just saw a fresh copy of my responses or my labels at the same features? Another way of saying that is that y star I is drawn IID from the law of yi given xi. Okay? You can think about this as saying I'm going to draw x and y. Here I'm just going to draw y. Leave the x's as what they are. And if x is fixed, then this is really, you could argue is the most natural notion of risk. Yeah.
So y star is going to be f of x plus a new error term. So is trying to minimize that the same as trying to make f hat match f?
Yeah, great question or great point. In fact, I had meant to reserve risk and error for equivalent metrics, but with slightly different definitions. So I meant to call this error, prediction error. And what you talked about, I meant to call risk, which is exactly the point you made. Can you guys see if I write down here, or should I move on to this board? This is fine. So in both models, the error is actually equal to a constant that does not depend on f hat plus a different notion of accuracy, which I'm going to call risk. So this is exactly what you asked. Is it equivalent? And the answer is yes. It's equivalent to measuring risk against the true regression function plus the noise level. Sorry? Yeah, I don't know why I keep writing error and risk. Thank you. These are supposed to both be risk. Okay, so yeah, here I would just take f to be the conditional expectation of y given x, and I would take sigma squared to be the marginal variance. So it's the variance of that residual. So in both cases, this is true, and that means it's equivalent to think about getting close to f or being able to predict y well on y star or y0. Yeah.
Also, you're supposed to think that f hat is also a random variable that even in the fixed x case is random.
So the expectations of everything that's random that's not being conditioned on. So I'm integrating over f hat and over the y stars. Okay, so yeah, go for it.
What's sigma squared in the context of a random x? Is it just the variance of y position x?
I define f to be expected value of y given x. I take the random variable y minus f of x, and I take the variance of that. Yeah.
So everywhere we're getting error at risk f, so that's also a function of big F, right?
Here it is. Here, you're right. So I think in some version of the notes, I don't know if it's still there. I sometimes put that explicitly as a function of big X, but just for kind of easy, less things to write, I'm not putting that explicitly.
And then for risk, the f hat is really the algorithm that outputs f hat, right?
Yeah, this is very common in stats, but it's an abusive notation. It's really exactly what you said. There's some algorithm that outputs f hat. I'm measuring the error, the risk of that algorithm.
We can't say anything about if I give you UX.
Are you asking, like, if I knew something about this, I couldn't say anything about what would happen at a new x? So you're asking, does this being small imply this being small?
Yes.
Yeah, that's a great question. The answer is, well, I have an answer that I'll get to later, but the answer is, it really depends on the smoothness of the problem and the dimensionality. So that's a big part of like classic stats literature.
I think in your risk and arrow F, you only care about the arrow on the given data set X. So does that mean you don't need to care about the structure of the X? Somehow like XI can
Which problem are we speaking about? This problem? You're asking, does this accommodate more feature models than the top one?
yeah, for the picture. So I mean, it looks like to me you just need to build a predictor for each XI, and you don't need to care about the structure of X.
I mean, that would typically be a bad strategy, right? If I really believed that somehow F had any smoothness at all, then I wouldn't do that, right?
Yeah, but in your ring and your arrow, I think, I don't know.
I mean, what you're saying might be true if I thought that F had no relationship between different x's, but that's not really typically what we would be using as a working model in for the types of prediction problems I'm thinking about.
Unless the risks include the sigma square.
Yeah, I'm sorry, guys. I just continue to. My error was correct, but then I should have defined that as risk. This is way too many. So what I meant to say is that these are notions of risk. Okay, I'm sorry. I should be paying more attention to what I'm writing. This is risk F, and this is supposed to be risk R. So risk is measuring proximity to F. Error is measuring proximity to Y. They're equivalent because they only differ by the noise level. So that means that like minimizing one is equivalent to minimizing the other. Comparing between models is equivalent, et cetera, et cetera. Okay. Sorry for so many backs and forths. This is just the statement I wanted to make. Okay, I should move on. But I think that was hopefully, we got some good discussion there. So, okay, actually, before I move on, I want to say one thing, which is that this might seem strange, but I think that there are good reasons why statisticians thought about this and have been thinking about this for a long time. And it's because I think a lot of the motivation for regression models and prediction came from experimental design. So if I designed the x's, if I was asking the question, how much crop would I grow, right, at various plots, as various parts of my plot of land, right, and I could actually design these x's in order to run this experiment, then what I want to know is next year at those same parts that I designed, how much crop would I see? And I'm in this problem. I'm not talking about some hypothetical new draw from some distribution. I'm talking about at the things I designed, right? And I think that there are still many problems that we have, and this is again something that I think we could talk about for half an hour. So hopefully I can make this comment, and then we can talk about it in the break. If you disagree with me, there are many problems that we have in statistical prediction machine learning. They're kind of between these two, and it's not clear that either model is appropriate. So let me give you one example that's a food for thought. Think about election forecasting. Okay, if I'm asking about forecasting the amount of votes that either candidate sees in the 2024 election, then if I'm doing that per county, then actually somehow those demographics are fixed. I know what they are, right? If I'm using demographics in my predictor. Other things that I'm measuring, they're probably also fixed. It's not really clear that this is the right model. It's not clear this is the right model either, but it's really somewhere in between. So, we could talk at length about how to map problems onto these frameworks. I just wanted to make the plug for experimental design as a motivation and put out the election forecasting example as food for thought. And like I said, we can talk more in the break about that. Okay, so let me now talk about the second part, which I'm going to call fixed X decision theory. So how do I reason about, an object like this, or about fixed X risk? This is a way that is done classically in statistics. And it starts off with a definition that people in this literature call optimism. This is what people in machine learning would call generalization gap, the gap between test and training errors. And because we're in the fixed X model, I'm going to use the fixed X notion of risk. So I'm going to say that the optimism of my predictor, I'm going to keep using the subscripts to denote which notion of error I'm thinking about and which model I'm imagining that I'm working in, the fixed X, the random X model. It's the difference between its prediction error in the fixed X sense. So how I would have done at some new Y's that were sampled at the same X's, minus the training error. And I'm actually writing down the expected optimism, because I'm going to take an expectation over the training error. But like I said, there are versions of this that are training conditional. I can kind of fix the training set. But I think I'd rather just keep things simple for now. Okay, so that's a familiar object somewhat, right? If this is large, then I should be somewhat concerned in the sense that I don't think that my training error is representative at all of what I expect to see in terms of prediction. Okay, now we're going to get into, maybe more philosophy. I shouldn't say concerning. Let's just say that if it's large, then I don't think that my training error is indicative of what I should see at prediction time. And okay, we saw yesterday Nati's talk, and we all know from having seen this before in classes and so on, that I can control something like this if I put a random X prediction error. I can control something like this using some kind of complexity measure, right? Like VC dimension, Rademacher complexity, and so on and so forth. So I could bound this in terms of the complexity of the class in which I'm scanning to find f hat. And again, that would be done typically with the training set treated as random. Here's a different fact about optimism in this fixed X model, which is that we have a very nice decomposition that I attribute to Brad Efron, but that's just because he's done lots of work on this. He attributes it to people before him. Yeah, there's a hand up here. Did you have your hand up? No?
Everything conditioned on the X one.
Thank you. Yeah, this is still supposed to be conditional.
Oh, why I instead of why I start? Sorry.
Yeah, this is training. This is the error at new Y's. Yeah.
I've been kind of confused about this term before. So optimism is when future is the same as the present.
And the features, not the labels, the features. Okay, if your labels are deterministic functions of your features, then that doesn't mean anything. But I'm in a model where there's noise.
Optimistic is when this thing is zero, right? It's
Yeah.
nothing. You have perfect.
Well, most optimism when this is zero. No, I would say that's the least optimistic. Yeah, I mean, optimism is viewed as a negative thing in this context. Maybe that's what's confusing you. Right? You're like overly optimistic that you'll do well at prediction time if this is large.
I see. Oh, okay.
So maybe that's the confusion about how the word, the polarity of that word. Yeah. Yeah. So, I mean, if you I'll give you some references from some of Brad Efron's work. So he has some papers on this. This is not his first paper on this, but it's my favorite paper is from 1986. It's called How Biased is the Apparent Error Rate of a Prediction Rule? So apparent error rate he was using to mean training error. So he just asked, how biased is the training error of a prediction rule? He had an example in which he was looking at a football kicker who had kicked from like various yards throughout the season. He recorded the number of successes at various yardages, and he fit a logistic regression model, which was predicting the probability of success given distance to the distance that the kicker was away from the posts. And then he said that has, in my training error, that had accuracy 70%. How biased is that? What should I be expecting? Okay, so this is the kind of problems that Brad was thinking about at this time. And this actually dates back even earlier to, he credits this idea to Akeike from AIC, Colin Mallows from Mallows CP formula. Both of these papers are 1973, and Charles Stein in 1981. And fun fact, this is being recorded, but I believe this is true, is that Charles Stein wrote this paper in the early 70s, but he was apparently he didn't think it was a very special paper, so he decided not to publish it and kept it in his office for a long time until some of his colleagues found it, including Brad, and convinced him to publish it. So this is a very, very nice paper that I'll talk about shortly. Okay, so what does this say? It's actually a very simple statement. This covariance formula, it's trivial to prove, is that we can actually write down an equality for the optimism that does not depend in any way, is not making any assumptions in any way on how we got f hat. So this applies to any predictor. This could be as simple as a logistic regression, if I was doing classification, or linear regression, or it could be random forest. It doesn't matter what it is. And that is that this is equal to twice the sum from I equals 1 to n. Let me erase this just for a second, of the covariance between yi, that's my ith training response or label, and f hat of xi. Again, treating x as fixed, so that's why I'm putting the conditional on x here. So this covariance is only over the randomness in the y's. Okay, so let's just look at this for a second. The more complex this predictor, the more self-influence, this is sometimes the word that people in the literature use, yi will have on its prediction, the larger this covariance would be. If this is not very complex, then it's not going to depend too strongly, right? My prediction for yi is not going to depend too strongly on yi itself, so this covariance would be smaller. But somehow this is measuring, this particular covariance is measuring the interaction between an individual label and its corresponding prediction in such a way that when I add it up over the training set, it gives rise exactly to the optimism.
That's the question.
Yeah.
So in that covariance, is the randomness over like the yi that's written there, is that the same yi that's labeling each?
Yeah, that's in training. So this is my training set. It's the same one here. So it's the same one here. This is training error.
So there's a y influencing both the f hat and the y.
Exactly. Okay, so I'm going to prove this for you guys. It's very simple. I'm actually going to prove something that's slightly more complicated, but that's also simple to prove, which will show you that this is true for any Bregman divergence. So this is going to cover logistic regression, the most natural loss we'd use there, and other problems as well.
Sorry, I don't follow the definition of the expectation there. This is just a randomized y, right?
Correct.
And then the error f, the way you define it, it seems to, because you have clauses. Oh, I'm looking at the definition at the bottom.
This one?
Yeah. Isn't that the definition?
They're the same?
Yeah. So your little f, that's the conditional expectation.
Right.
And so you're adding close the sigma squared, so that's already the expectation of yi minus f.
No, that's only true if these somehow were independent. They're not somehow, right? So this decomposition is true because I'm looking at something that's independent of what I used to train, right? Because then I could add f of xi and subtract f of xi. I would expand the square, and I get this, and the cross term 0 because of independence. Once I have this, it's no longer the case. Because I've used yi to fit f hat, so there's dependence there. And actually, the cross term is this somehow. That's what we're doing. We're doing that same kind of decomposition, and we're just keeping track of the terms that are not 0. Another question? Yeah.
In the random X model, does f of x still meet expectation of y given x?
Uh-huh. Okay, so here's the proof. I'm going to maybe prove it over here now. So, okay, the easiest proof is what I just mentioned to summary, which is that I could, maybe I could start with, it's very similar to what I mentioned to Sam. I could start with this definition. I could subtract yi and add yi. Okay, expand the square. One of those terms is going to look like yi minus f hat of xi. That's training error, right? The other term I'm going to be keeping track of is this after I expand. That's basically the proof. But there's a slightly different way to see it, which I'm going to show you, which will also generalize this fact. And this is I'm going to give a couple hints that somehow, like I said, this is everything I say is going to be true for Bregman divergences. So this is one of those hints. So let's suppose that instead of looking at squared error losses, let's suppose my loss was measured as a Bregman divergence with respect to some potential function phi between points u and v. So here u and v are univariate. So that's the Bregman divergence. If people, I think probably many people have seen this, but in case you've not seen it, then I can think of this as I have some function phi. This potential function we typically assume is convex. And I'm looking at 2 points. And I'm going to take the first order Taylor approximation to my function at v. I'm going to ask what's the difference between its actual value at u and its first order Taylor approximation at u, and that's what this Bregman divergence is measuring. Okay. Here's a fact that I learned by rereading Brad's paper, by the way. I don't know that this is common. So this type of loss can encompass all the deviance functions, which is the statistics term for negative log likelihood that we would use in exponential families. That is, I think, well known. Here's a fact that I didn't know until I reread his paper. I can actually get 0-1 loss out of Bregman divergence. So, yeah, of course, phi can't be convex for that, but I can get 0-1 loss out of it. So let's suppose that I'm going to be measuring Bregman divergence between yi and f hat of xi. Okay, if I take phi to be, if this is my prediction, let's say for the probability that y is 1, if I take phi of u to be the max of u and 1 minus u, then you can check the calculation to that. And this function looks like this. So here's a half, here's 0, and here's 1. Okay. Wait, that's not what I wanted to write. I think I wanted to write, that does look convex. I wanted to write min. So the problem is that Brad reinvented Bregman divergences without knowing that. And he actually parameterized this by the negative of phi, which he assumes is concave. So I have to flip the sign everything he did. So I think it's probably this one then, which would look like this, right? So we can do the calculation, and we'll see that this is actually 0-1 loss. Okay, so you can get more out of Bregman divergences than just deviances for exponential families.
What do we do with the derivative at 1/2? We just define it arbitrarily.
Yeah, I think that what he does is he just basically doesn't treat what happens at 1/2 at all. So basically assumes that your predictor is never going to output 1/2 or something like that, because y will be binary, right? So, okay, so this is a Bregman divergence. Let me now, okay, let me point out that you know, I can of course get squared error from this, right? That's what we were working with originally. So this is the way I'm going to measure the loss at a point xi. What would I take for squared error as my potential function? I would just take phi of u to be u squared, right? And I'd get squared error out of this. So now let's just look at the difference between Bregman divergences at, shouldn't say minus, at yi star and yi. So I'm going to measure this. This would be the optimism or the generalization gap if I was using Bregman divergence as my loss instead of squared error. So what are we going to see? We're going to see that actually this term cancels between the two because that's common, right? As is the product of this term and that term. So what I'm going to be left with is just phi of y star minus phi of yi minus phi prime f hat of xi times y star I minus yi, if I got the signs right. And now let's take an expectation of this, because remember I defined optimism by integration over the training set and everything. So what happens when I take an expectation? What happens to these terms? Exactly. So these cancel once I take an expectation. Right? And okay. What else can I do? I can add and subtract f of xi in here. Right? So if I add and subtract f of xi, add and subtract f of xi. So if I look at yi star minus f of xi, right, and its expectation against phi prime of f hat of xi, what happens there? Right, so I have a minus phi prime f hat of xi times yi star minus f of xi. And I have another term for yi. F of xi is the true mean. So what happens to this first term? It's 0 because of the independence between yi star and the training set. And I just get that. Okay? What is that? That's actually the covariance between phi prime of f hat of xi and yi. Right? It's exactly the covariance. And so we've actually proved something much stronger. Okay, let's see if we can recover that result. When phi of u is u squared, phi prime is 2 times u, so I get twice the covariance, which is what I claimed over there. It's exactly what I claimed. We've actually proved a per instance version of this optimism result. The optimism at each individual training point is given by the covariance between that training response and this function. Okay, so it's much stronger. It's like we can actually ask how much I should expect to be optimistic at every individual training point. And like I said, we could write down results for logistic losses and other stuff just by taking phi appropriately, even 0-1 loss. Although I have to look back at that because I'm slightly bothered still by the fact that Brad's paper treats 0-1 loss in this way, just because it seems unfamiliar, but I think it's an interesting thing to look at as well. Okay, so that is the optimism theorem. Yeah. This just means 0. That's the true f, right? So I could just subtract its mean here and it wouldn't matter. Yeah, good question. Okay, so I think this is interesting in its own right just to look at. And of course, now what we could say is that if we could estimate or bound this quantity, then we'd have a sense of what to add to the training error in order to get an estimate of prediction error. Right? That was like a lot of the focus of the development of this theory, was not to stop here, but then to ask, what can we say about this quantity? Okay, but I just so far wanted to highlight this as a fact that is somewhat complementary to the types of stuff that we think about in machine learning that we saw yesterday in Nati's talk. Because certainly the complexity of f hat, like I said, is going to make a big difference in this covariance. So let me, in the last 10 minutes, try to get through degrees of freedom and Stein's formula. And then I think that'll be a good stopping point, and we'll pick back up in the afternoon. So degrees of freedom, this is now just a definition. There's nothing that's particularly deep about this definition. Once we've seen that covariance formula, this is sometimes called the effective degrees of freedom. I actually could not trace back that well where this terminology came from, but I think it, and it wasn't in Efron's 1986 paper. I think it actually originated with some of the work on GAM, on generalized additive models. So this is Trevor Hastie and my dad. I think it's possible that they started using it in their book, and then that's what people started using afterwards. But I'm not totally sure of that. I just couldn't find a reference for where we started calling this next thing I'm writing degrees of freedom so ubiquitously. But here's the definition. If you give me a predictor, I'm going to actually take this covariance, and I'm going to divide it by 2 times the noise level. Well, no, I'm going to divide this quantity by 2 times the noise level, so I'll get rid of the 2 there. I'm going to call that degrees of freedom. Okay, so where does that name come from? The name comes from the fact that for certain models, like we're going to do the calculation together just now, this is truly the number of free parameters that I am fitting in that model. So for least squares regression on linearly independent features, we're going to see that this is the number of features. Okay, and I think that the degrees of freedom name comes from the fact that for linear smoothers, somehow there's like an analogous formula, and it ends up looking like something that we would usually use as the degrees of freedom in an F-test for some good as a fit for that, for some hypothesis test that we do with that linear smoother, and so that's where the name comes from. But think about it as the effective number of parameters that we would fit, that we're fitting with F, okay? And we'll have some more evidence for why that's like, this is just anecdotal. Like I can compute this for you for various predictors, and we can see that it makes sense. But what we're told is that actually from Efron's covariance formula is that if I were to take the training error, I have this in hand after I fit the model, and I were to look at 2 times sigma squared over n times an estimate of the degrees of freedom of my predictor, right? Then this would be an estimate for prediction error. And if this was unbiased for degrees of freedom, then this whole thing would be unbiased for prediction error. That's somehow part of the power of the covariance formula. Okay, I've just changed notation so that I've talked about estimating degrees of freedom rather than estimating covariance, but it's really the same thing.
Optimism formula has a divided by n or something.
Yeah, thank you. Yeah, and we just did like the per data point calculation. So you add up and divide by n. Yeah.
So your estimator, your DF hat.
I haven't told you how to do that yet.
Okay, but that's going to be an empirical estimator based on, because F hat is really a learning algorithm, not a vector, right?
Yeah.
In what ways DF hat a function of F hat, or is it really just? It's also a function of the data, presumably.
Exactly. We're going to want it to, I mean, this shouldn't be using a holdout set. If we estimated this with a holdout set, there'd be no point. So we're going to try to get an estimate of this from the training set. And like this question or comment that was made earlier, every time I write like function of f hat, I really mean a function of the algorithm that produces f hat. Somehow like, you know, think about f hat as being least squares. It's not like the actual fitted least squares model. It's the algorithm that runs least squares of y on x. So in the last 5 minutes, okay, I want to do 2 things super quick. I want to calculate this for you for least squares and for k-nearest neighbors regression. We're going to, in both cases, conclude that it's intuitive. And then maybe I'll have to end because of time. And maybe I'll tell you Stein's formula later whenever I talk. The preview for later then, Stein's formula is a way to estimate this. Stein's formula gives us an unbiased estimator for this quantity. And it's very general. It doesn't apply to all f. It assumes a smoothness condition on f hat. It's not always computable, but it's a very general result. If you're willing to think about your predictor as being smooth in some sense in terms of its dependence on the data. And Stein's formula would also reproduce all the results that I know how to compute by hand, like these 2 I'm going to show you now. So that's going to come later. So let's do least squares in KNN, and then I think that'll be it. Least squares regression. So I'm going to write down X as my feature matrix, just because it's more convenient that way. So I've taken these xi's and I've put them into rows of this matrix X. And I write down Y as my vector of responses. So least squares of Y. And I'm going to assume this is really important for what I'm about to say. It doesn't cover all cases, of course, and this is going to be, you know, one of the. I'm going to come back at the very last section, which I didn't write down. I'm going to try to criticize some of this framework and talk about ways to think about it differently and some extensions. And this will be one of the points of criticism, is that I'm going to assume that X has linearly independent columns, which means that I cannot be in a situation in which P is bigger than n. Right? I must be in a situation in which P is less than or equal to n for this next fact to be true. Although we'll see immediately what happens when P is bigger than n, and we won't like it. So it's not that the calculation can't be done. It's just that it doesn't make much sense. So f hat least squares is the predictor that returns X transpose beta hat least squares. These are my least squares regression coefficients. The regression coefficients are given by X transpose X inverse, X transpose Y, right? So now I can ask you, okay, so a little more notation. x beta hat least squares. So now I'm taking my vector of my matrix of features and I'm multiplying it by the coefficients. This is going to give me a vector of predictions at the training points. So this is going to give me the vector of f hat x1 through f hat xn. This is equal to just multiplying this expression by x. I can think of this as the projection matrix onto the space spanned by the columns of x, right? And now if I want to compute degrees of freedom of f hat least squares, what is the answer to that, right? That's what we want to figure out. Well, I can actually rewrite this formula in a way that's slightly more convenient, which is that I'm going to take the whole covariance matrix of y and the vector of predictions, which is x beta hat least squares. And I only care about the trace of that, which is the covariance between yi and f hat of xi, right? I don't care about the off-diagonal elements. That doesn't appear in this formula. And I take an expectation. No, the covariance, sorry, is already, yeah, it's already done the job. So there's no expectation I'm taking. Trace of the covariance, OK, sigma squared. So this is quite easy to compute. Once we think about it in this way, I'm taking in the trace of y and the projection matrix onto the space spanned by the columns of x times y. OK, covariance is a bilinear form, so I can just take this px out, right? Oh, and everything here is conditional on x, which I failed to write, but that's really important for this calculation. Conditional on x, right? Conditional on x. So what's the covariance matrix of y? The variance covariance matrix of y, conditional on x? What is that going to be? In our fixed x signal plus noise model? It's just sigma squared times identity. That's just the independent errors, right? Assumption. So now I get the trace of sigma squared I times px. I've taken the p out, and I've just looked at the covariance of y with itself, conditional on x. And the sigma squares cancel, and I get the trace of this projection matrix, right? I can use sometimes called trace rotation. I can move this x transpose up front, and I get x transpose x inverse, and that gives me the p by p identity matrix, right? So the answer is p. I take its trace. So the degrees of freedom of least squares is just a number of coefficients that we fit. It's very intuitive, and I think that's the OK, so let me say just a couple more things about this. This result was actually already known in 1973. It was somehow established independently by Colin Mallows and Ike. So this is also the kind of driving result for AIC, for people who have heard of that criterion. And well, what do we call this then, right? What is the name of this estimator in the case of least squares? It's the training error plus 2 sigma squared p, the number of predictors. That's called Mallows CP estimator. Thank you. I keep missing that, divided by n. Mallows CP estimator 1973. So this is just a generalization of that, what I just talked about with covariance and Stein's formula and so on. Okay. I'm right at time, but I think KNN we can do actually even quicker. So let me just do that for you, and then we'll quit. So KNN I can think of as the estimator that takes a weighted average of my y's, where the weights are either 1 over k or 0. Right? And this is if xi is 1 of KNN of x, and 0 otherwise.
KNN stands for the k nearest neighbors.
K nearest neighbors regression estimator. Yeah. Okay, so let's now just call the vector of predicted values. Let's call this whole vector equal to a matrix Lx times y, where this Lx has rows that are equal to W of x1, W of x2, W of x3, and so on, right? It pulls out the weights that I need to make predictions at the training points. This same calculation, okay, we're going to get to the same step that we had here. So if I want to know the degrees of freedom of the k-nearest neighbors regression estimator, I'll pursue the same steps, except I'll get to a step where I say, what's the covariance between y and Lx times y, where that's this matrix that pulls out the weights that I need to make predictions at each point, conditional on x. Okay, and I'm going to use the exact same arguments to conclude that the answer is going to be equal to the trace of this matrix. So now this actually is true for anything that has this form, which includes things like RKHS estimators, smoothing splines, other things as well. So we have the formula for all of them. It's just the trace of what we call the smoother matrix. And for k and n, the answer is going to be equal to n over k. You can check that's the answer because yeah, the diagonal elements are all 1 over k in this matrix, right? So when k is 1, the degrees of freedom is n. I'm basically fitting a parameter per data point. It's the interpretation. When k is n, I'm fitting an average. So I'm just fitting 1 parameter. So the intuition checks out. Okay, I think I should wrap up, and I guess I'll continue later. So thank you, guys.
Maybe in the interest of time, we'll take one question and take the rest offline. Yeah.
Is it, for example, if you did the thing that you did for the 0-1 loss, does the covariance formula give you back Rademacher complexity or something like that? It seems morally similar.
I don't think it can give you back something like that. I mean, I agree that there's, Rademacher complexity is measuring the kind of correlation between noise and your function, right? But I don't think it can give you back something like that in this, exactly, yeah.
It's a big difference because this is for a specific predictor.
Exactly.
Exactly. The predictor is ERM over a function class.
The what?
The predictor would be ERM over a function class. That's still.
There's no student.
I mean, ERM would have.
You take the difference. You have to choose difference and take least of the noise. Anyway, we can proceed.